So, last time we've seen how to set up Truffle, how to set up Infura, how to configure our network, and how to deploy a contract on the development network and on the testnet. Today we're gonna create an ERC20 token. So basically we're gonna create our first cryptocurrency. It will work on the Ethereum network, and the code required for that is actually just these lines of code here. We're gonna use OpenZeppelin to deploy our cryptocurrency, and we're gonna go through some terms used in the crypto world regarding ERC20 properties. So first of all, supply means the amount of coins that are out there that are created by a smart contract. Mint means to create tokens to insert supply into circulation. Burn means to remove tokens from the circulating supply. And cap means a limit to the maximum amount of tokens that can be handled by our contract. So first of all, we're going to create a standard ERC20 token, and to do this we just need to import this ERC20.sol contract from OpenZeppelin and create our constructor and call it when we deploy the contract. To go through what functions are allowed and are offered by OpenZeppelin, I'll open this contract and walk you through what can be done. This is the constructor of the ERC20, in which the contract saves the name, the symbol, and by default it uses 18 decimals. Solidity has only unsigned integers, and in order to have something like 0.2 tokens, you will need to add some decimals. So basically, in order to have 0.2 tokens, you will actually write 2 followed by 17 zeros. Moving forward, we got some getters here to get the contract name, the symbol, the decimals, and the total supply. This is a balance of function which queries how much tokens does an address have. Here we have the transfer function, which can be called to transfer from the caller to a specific recipient. And here we have the allowance. The allowance concept is basically used in order to allow another address to transfer your own tokens, and this is needed in some cases where a contract needs to access and to spend your tokens. For example, if you want to trade your token on Uniswap, you need to give access to the router contract to spend your tokens in order to exchange them for another ERC20. And by calling this allowance with the contract of the by calling approve, because allowance is a simple getter in which you can check the allowance, but by calling the approve function for a specific spender, you allow the spender to move your tokens around from your own address. You have the transfer from function, which the spender which you allowed to move your tokens can actually transfer them from your address to another recipient. You can increase or decrease this allowance. You can you have here also an internal transfer function. Internal functions can be called only within the current contract and the contracts that it inherits from. So basically you cannot call this function from the outside world. The mint function is the function that allows the contract to place tokens into circulations, and same with the transfer function. The underlying mint function is an internal function which can be called only from here or from the contract that inherits this one. The burn function effectively removes supply from a specific address, and the same is available here. So it's an internal function that can be called only from this contract and the contract it inherits from. Same with this approve function. The setup decimals changes or sets up the number of decimals used for this token. In general, for ERC20 tokens, the number of decimals is 18. And this before transfer function is a function that can be overridden by another contract and do stuff before it calls the actual transfer function. So there we go. We have the constructor to build this ERC20, and what we need is just to go here into the initial migrations and specify the parameters with which we can call the constructor. So in our case, the name will be SolTouch coin, the symbol will be Sol, and we will have 1000 tokens available into our address when we deploy the contract. This is because in the constructor we call the internal mint function, which increases the balance of the deployer of the contract with 10 to the 18 times the supply specified in the constructor. So let's go ahead and run the command to migrate on the testnet and see what happens. I have an old Sol coin test here, so I'll remove this. It's compiling our contract. I feel like I should also specify the types of functions, because we've discussed the internal function type. This can be called only from our contract or the contracts that inherit from it. We also have a private function type which can be called only from the current contract. So basically, if we had a private function here, we wouldn't have been able to call it from the other contract as opposed to the internal function. We have public functions which can be called from the outside world and also from the current contract and the contracts that inherit from it. And we have the external function type, which can only be called from the outside world. It's pretty important to specify functions as external if you are able to do that, because they cost less gas when they are called. So if you have a function that you never call from the contract itself but only from the outside world, I suggest that you declare it as external, because it will cost less, because it doesn't save the parameters with which you call it into memory of the contract. So it automatically costs less gas. So we have had some warnings here which state that some constructors don't need the public keyword because they're implicitly public. We don't need to worry about this wording right now, and also something that tells us to specify the license. So we went through the dry run, we went on to the actual deployment on the testnet, and we deployed the contract at this address. We can now go to MetaMask and go to personalized token, and it will automatically find our contract, our symbol, and it will add it to our list of coins. So right now we have 1000 Sol coins that we can spend, we can allow others to spend, and do the basic functionality that an ERC20 has. So that's it. That was everything required for the creation of a very standard ERC20. We might want to explore a little bit more and make this token mintable and ownable. What ownable means is that this contract will have an owner that will be able to do some special stuff. If we inherit the ownable contract from here, we can see that in the constructor of this secondary ownable contract, an owner is set, and it's set as the address who deploys the contract. What we're interested in here is this modifier. A modifier is applied to a specific function in order to execute some code before or after the function finishes. We can see here that the only thing that included in this modifier is a verification that the caller of the function is actually the owner of the contract. You might wonder what's this sign here, and this represents where is the other code executed from the function that we're applying the modifier to. So for example, let's say that we want to give the owner the capability to mint supply, to insert supply into the circulating supply on a specific address. So we're gonna have to do something like this. We're gonna have to create this special function which takes as a parameter an address on which the owner wants to add supply, and as the second parameter, let's say we want him to add an amount of that specific supply. First of all, this has to be a public function. I'll set it for public for now because you might want to call this mint in other parts of the contract, but for all intents and purposes it can also be an external function. Then we'll have to make sure that this function will not be called by anyone else other than the owner. So in order to do that, we're gonna have to write this only owner modifier here. And in the function itself, we're gonna call the internal mint function from the ERC20. So basically this one here, which takes as a parameter an account and an amount. The account is our user and the amount is our specified amount. So that's it. Now we have a function which allows the owner of the contract to mint supply, to insert, to add the balance of a specific address and add some coins to that specific address. So let's pretend for a moment that we have this function in the contract, but we don't want the public to get concerned about the fact that the owner can mint infinite supply. So what we want is to assure the users of this token that from some point on not even the owner will be able to generate additional supply. So in order to do that, we're gonna have to introduce a cap, and we have this Open Zeppelin library which is suitable for this. So basically we can inherit from ERC20 capped. I remove the ERC20, the simple ERC20, because the ERC20 cap already inherits from ERC20, so that wouldn't be needed anymore. And I will place here a variable which is the cap, and now we can specify a cap for this token, and that cap will be an absolute limit to how much tokens can exist at some point in time. When we do this, base constructor arguments given twice, wrong argument. Okay, let's see what's the issue here. So we have the initial supply, we have the cap, we call the ERC20 with the symbol. Okay, now everything should be in order. So let's see what this ERC20 cap does. So first of all, in its constructor we declare a cap, and it's saved in the contract. It has a getter to see, to help users see the cap, and it overrides the before token transfer. So basically what it does, it verifies that after any transaction or before any transaction that transfers tokens from here to there, we make sure that the total supply with the new amount placed into the circulation doesn't get over the cap that we've set for this contract. Good. So we have an owner, we have a cap to our contract. Now we need to make sure that we also specify the cap here. We'll need to specify a cap with followed by 18 zeros. So 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3. Okay, this should be our constructor. So now I will deploy this on the testnet, and we're gonna have to also set up the Etherscan interface so we can easily interact with the contract, mint some supply, and make sure we don't get over the cap, and make sure that the cap functions. The same warnings are thrown about the visibility of the constructor. There's no reason to worry about those right now. We're into the dry run, and we're gonna be deploying on the testnet soon. In order to have a pretty interface made by Etherscan so you can interact with the contract, you'll have to tell Etherscan what is your code, and you'll have to upload it somewhere. That can be a slow process, so I am using this library here, which is called Truffle Plugin Verify, and I'll show you in a bit what it does. So this is our newly created contract. We can see it on Rinkeby, but we will not have any pretty interface at first. So when this will be made available by Rinkeby, okay, it's up. Here we'll only have this bytecode, and we'll need to verify and publish, and we would be required to upload all the dependencies in our contract. There is this nice library, Truffle plugin verify, which can be used to automatically do this when you actually deploy the contract. So this is the code for it. Instead of writing truffle migrate, we can write truffle run verify and the name of the contract. You'll need to go into truffle config and place here truffle plugin verify and declare it as a plugin, and also you'll need an Etherscan API key because it automatically uploads your code into Etherscan. So there we go. Our contract is now verified, and we can find the code at this address. It's a different contract because I ran the command first with migrate, and the second one I've ran with truffle plugin verify. So here we go. We have our code uploaded here, which contains also some libraries that we did not use. Nevertheless, for the purpose of this tutorial, they're not important. We have an owner to our contract, which is the address with which I've deployed the contract. So this one. This is the old Sol token, the one without owners and the one that's not mintable. So we'll need to place in MetaMask the new token contract. Okay, so now we have 1000 Sol tokens here. We're gonna transfer some of them to make sure everything is in order. Let's transfer them to the second account from generated with this mnemonic phrase. Transfer between accounts. Let's transfer 10 Sol tokens from the first account to the second. Okay. So now let's wait for it to transfer. Waiting. Come on, testnet. Did I place a small fee for this transaction? Should have been done by now. Okay, so it's included in block. It should be done shortly. Oh, oops. It failed to transfer. Unable to check with sender. Yeah, I placed very little gas for this transaction, so I shall do this again and not be a cheapskate with testnet gas. So let's transfer 100 Sol. Confirm. Sending. Still sending. Okay, done. So now we have in the second account, if we switch to the second account and add the contract here, we should have 100 Sol. Good. Then the next thing we want to do is to verify that we can mint some supply. So the upper limit, the cap of the contract is 2000 Sol tokens. So we're gonna try and mint 1000 more, which should be allowed because it adds up to 2000 tokens, but we shouldn't be able to add any more other than this supply. So I'm gonna use my account and mint them on my address. I've called the mint function. I am the owner of the contract, which you can check here, so I should be able to do that. If you're not the owner of the contract, this function should throw an error, because when we defined it, we place this modifier here. Okay, so now I have 1000 more Sol tokens, and this should be the upper limit, because there are 2000 Sol in circulation right now. 1900 are on my first account and 100 are here. So if I'm the owner and I want to meet just a tiny bit more, a fraction of a Sol token, I shouldn't be able to do this. So this should return an exception in the code, and if I confirm this, the network should reject it. So this is it. Basically, this is all you need to know to deploy a standard ERC20 token to the testnet or mainnet. It's not more complicated than this. There are a few tweaks and few customizations that you can do on top of these functions, but this code here is enough to get you started with your own crypto token, is enough to get you started and launched on the mainnet so you can interact with other ERC20. From here you can add liquidity on Uniswap and start selling the token. For everyone out there who is buying ERC20s, be careful and do a lot of research before you go ahead and throw your money in any coin, because as you've seen, this is all the code required to write an ERC20. So basically anyone can do it in a few minutes. Make sure to know the team behind the project, make sure to read their white paper, make sure to look at the code and do some serious investigation when you're investing into a newly created project, because it's, as you've seen, is very, very simple to get started and create a token of your own, and pretty much any programmer can do it in few minutes. That's all for today. Thank you for watching, and if you find this course useful, then click the subscribe button. Thanks.